a subroutine which consisted of 3 nested loops and which actually does generate 4095 bytes of data. And most interestingly, it contains a test against this value. And when you check, for example, Wikipedia on LFSRs, you always need a generator polynomial, and only certain ones of these generator polynomials are actually generating a maximal LFSR. Well, and this one is one of them, so we were pretty certain at that point that we had found the key stream generator. Sorry. Okay, so one other interesting question is where the 16-byte key, which we found pretty much in the beginning, fits in, because the key stream generated by this LFSR is actually always the same. It just starts with some initial value, which is hard-coded in the data and generates 4095 bytes of data. Actually, it generates 11 times this amount in order to be able to use the buffer more efficiently, so you don't always have to wrap around. But in any case, the random number hasn't been used up to this point. So what we at first were a bit surprised is that the LFSR data also generates a reverse mapping table, which gives you the offset for each value, for each random number, basically. And so the starting offset at which the encryption begins is taken from this reverse mapping table. And the index for this table, again, is generated from the key. So the key simply tells you where to start in the actual key stream. And this is also obviously how the device itself works then. The CRC of this key is just fed into the LFSR on the device, which then starts generating the same key stream as in the driver. So this is, in fact, a standard CRC12. And it looks like the device doesn't even generate the data, doesn't even generate the entire key in memory, but just always pulls a single value from the shift register and then advances it by 1. Okay, so one interesting piece is, of course, that LFSRs which are loaded with 0 will always output 0. So if you have a CRC12 or 0, this should just disable the encryption entirely. For some reason which we haven't been able to figure out yet, it doesn't work with every key, but there are some keys which do have a CRC12 of 0 and which do disable the encryption, and we found these in the driver, basically. Most importantly, they are in the driver because the driver has a debug flag which just turns off the entire encryption if you set it to 1. So in fact, we might have found this earlier, but it's still funny to be able to decrypt the earlier captured data. So, okay, so at this point, we were now able to capture unencrypted communication between the device and the Windows driver. And so we were now able to start having a look at the graphics protocol. The protocol itself is in fact quite simple. I won't go into much detail here. So the most important command is just this graphics command. This is more or less the base value. And you have 2 flags which can be added, and you have 3 subcommands. Most important are these 2, basically. The device internally is organized in 2 separate frame buffers. So you have a 16-bit frame buffer, which is used in 16-bit color depth and in 24-bit color depth. And when you use 24-bit color depth, you get a secondary 8-bit frame buffer, which delivers the missing 8 bits of color data. Yeah, and you have basically just linear memory in the device, 16 megabytes. You can do copy on device. You can write data in a certain RLE, run length encoded. Well, not too efficient encoding, but this is, for example, used by the driver to clear the frame buffer. So for big runs of similar colors, this is quite efficient, in fact. And you can, of course, just write raw data to the device. And every one of these commands is followed by a 3-byte address, and 1-byte pixel count. This is in fact quite important. This is not the count of bytes which follow, but it's the count of pixels which are in the end written to the frame buffer. So for example, for the run length encoding, you get a much higher pixel count than what's actually following in terms of data. Okay, there are also some auxiliary commands. You have a number of registers which for example, to determine where the frame buffer starts, so you can do vertical scrolling by just setting a frame buffer offset. Most of these values we have just taken from what the Windows driver sends to enable standard video modes, so these are the blanking, offset, and so on values. There's a flush buffer command, which causes probably all queued commands to be executed. And there's one very important command which sets the Huffman encryption table. Yeah, as I said, if you're interested in more details, please see the references. Otherwise, I think it would be pretty boring. Now I'll come to a small intermission, which is how DisplayLink, the corporation who manufactures these things, reacted to the entire stuff. So this was this first reverse engineering steps happened about almost exactly a year ago, in fact. And for half a year after that, nobody pretty much looked at this stuff until somebody else, Roberto de Ioris, started writing an Xorg driver. And suddenly DisplayLink started, we're going to release our great open source library, which is called libdlo, and which is open source but has two big shortcomings. The init sequences were in fact still encrypted, so there were still just big binary blobs which were dumped to the device. And the compression, especially the Huffman-based compression, which is the defining feature more or less of these things, was still missing. So at this point we decided that we would have to figure out the Huffman compression by itself, or by ourselves, and started to have a look at this. I already mentioned the run length compression. The Huffman compression, with something like gzip uses, is of course much more efficient for picture data. Instead of the run length compression might actually work quite well for things like desktop images or just user interfaces. But as soon as you get pictures or video, the Huffman compression, of course, is much more efficient. One thing which I also already mentioned earlier is that there is a 4.5 kilobyte binary blob which is sent with this command, and this command occurs nowhere else, just in the initialization with this blob. And if you leave this command out, the device still works as it does otherwise, just compressed data doesn't work anymore. So this is pretty certainly the Huffman table. And okay, so looking at this table didn't really yield much results, so we started again by just analyzing data which we sent from the Windows driver. So the two most basic results were that the pixel values aren't encoded themselves, but the difference to the previous pixel. And when you start a new command, the previous pixel is set to black, so to 0. And the second finding was that bit sequence of 0 bits encodes a difference of null. So this is also in Huffman compression, shortest sequences correspond to the most frequent numbers. And of course, in images, as you have pretty much often, you have runs of similar color still. 0 is the most common difference value. Now, the next step was to just treat this as another crypto problem and find the table again, which gives you the Huffman sequence for a certain pixel value, or rather difference value. And so we just tried basically a chosen plain text attack, which means we just send a suitable color pattern through the driver, through the Windows driver, for every difference value which might occur in the data. As the device